Welcome everyone to this new SIPTA talk of March. So we skipped February, but so this new SIPTA talk will be given by Arthur Van Kamp, but I will let Jason introduce Arthur in more details and chair this session. So Arthur will talk about independence and choice functions, and you can see that our next seminar for the April seminar will be actually in May, given by Marnik Swillian. We don't have the title, but Marnik works in decision processes and Markov decision, robust Markov decision processes. So this is likely to be the topic of the next talk. To chair this session, I invite Jason, that knows Arthur very well, to chair the session. So Jason, you're up.
Well, thank you. I will keep this brief. Many of you know Arthur very well. Um, there are too many good things to say about him to be able to say them all here. I'll just mention he grew up around Hert and Jasper and Kike as part of the Foundations Lab in Ghent, and went on to work with Sebastian as a postdoctoral researcher, and then joined me and Kevin and Katrin and others here on the EPIM project for many years. And now Arthur is an assistant professor at Eindhoven in the Uncertainty and Artificial Intelligence group. He's done a ton of beautiful work on the foundations of choice functions and desirability and on IP scoring rules. And apropos of that, I mean, and on top of that, in in addition to being one of the most incisive minds I've ever come across, he's got the biggest heart that I've ever known. So uh, it's a real pleasure to be able to spend time with him and learn from him. And apropos of his research, he's going to tell us a bit today about the right notion of independence for choice functions, or at least a good notion. So take it away, Arthur.
Thank you very much, Jason. And thank you very much also the organizers, Jasper, TK, Sebastien. Good afternoon. Thank you again very much. I'm very excited. I'm slightly worried to talk about choice functions and a good notion of independence for them today. What I will talk about today are two main things. The first thing is belief models, or perhaps more accurately, models that describe how you act in the fate of uncertainty. That will be choice functions, but also the equivalent model of sets of desirable gamble sets. I will also talk about sets of desirable gambles. And I will introduce three notions of independence. One is by me and my co-authors. Two have been around already for some time. And I will try to contrast them somehow. So that's the program for today. And just to gather the ideas, what do we mean by independence? Well, I typically mean stochastic independence or a generalization thereof. So typically to fix the ideas, consider two random variables, x and y, and each takes values in a finite possibility space, just for simplicity. And so we have a joint mass function P, or P index xy. Then typically x and y are called independent with respect to P if this joint mass function, joint PMF P, factorizes into a product of two marginals, Px times Py. Now, of course, if all the probabilities involved are strictly positive, then by using Bayes' rule, we obtain that the conditional probability of x given y should be equal to the marginal probability of x, and the same vice versa. So the conditional probability of y given x should be the same as the marginal probability of y. And so this is equivalent to independence. So this already gives us this leads us into thinking into one way about independence, namely, independence should mean that if we learn about y, for instance, we learn that y takes a certain value small y, then this does not change our beliefs about x, and vice versa. So that's one of the three main ideas that I will talk about. The two other ideas are, to my mind, equally plausible. Let's try and put them all. Yes, here they are. And the two other ideas are, the second one is there is an independent representation. So sometimes if we generalize probability mass functions to more expressive, imprecise probabilistic models, these models might have a representation in terms of simpler ones. One requirement of independence can be that this representation, well, should consist only of independent models, simpler models then. That's also, I think, a plausible interpretation of independence. And the third one, I think, is introduced by Teddy Seidenfeld and later developed by Jasper de Bok and Gerte Koolman. And it's equally plausible to me. It says, well, it's unreasonable to spend resources in order to use the observed value of y to choose between decisions or to make decisions that only depend on x and vice versa. So that also seems a good description of independence to me. So these three thoughts will be the theme of this presentation. It will consist of two main parts. The first one, I will talk about the models, the belief models or the decision models, if you like. Mainly sets of desirable gambles and choice functions, or the equivalent sets of desirable gamble sets. And then in the second part, I will talk about independence for these choice functions. Now, because these models all work with gambles, or at least in the way I think about them here, it will be useful to now introduce gambles already. So the idea of a gamble is what? We have a random variable x, meaning we don't know the outcome of x very well, but we know that the outcome belongs to a finite set calligraphical x, the possibility space of it. Then a gamble is just a real valued function on x. We interpret this gamble as a risky transaction in the following sense. If you have a gamble f, then you're engaged in the following transaction. First, the real value of x is determined, and then your utility, your capital if you want, gets changed by f evaluated, by the gamble f evaluated in this real outcome. So by this real number. But be careful, this real number might be negative, so you might lose utility or you might lose capital. And so in this sense, a gamble is a risky transaction. But the gambles have they have an advantage, namely that they form a linear space. In a linear space, we call them L. And just as one example, if we have, say we have a coin toss, in which case there are two possible outcomes, heads and tails. And so in this case, a possibility space is a binary set. It's a set of two outcomes. And that means that gambles on this possibility space are two-dimensional vectors. So you can draw them. So for instance, this point, this dot, this vector is a gamble f, and we read its values here and here. So this is a value in heads, this is a value in tails. And it's a vector space, well, because we can scale every gamble by every real number, and then we get something on this line. And also we can, of course, add two gambles, f and g, in a normal vector addition way. Now, it's an ordered vector space, or an ordered linear space. And by this order, this is dominance order, maybe simple dominance order. We say that G dominates F, indicated by just a normal greater than. Well, if G is at least as good as F everywhere, and there is some outcome X for which G is strictly better than F. So that's the gambles G for which G dominates 0 is indicated in this green area here. These are the non-risky gambles, if you want. These are the good gambles. The gambles that make you win, or that can never make you lose, and make you win in some outcome. Now, on the opposite of this, the negative orthant, those are the bad gambles, because these gambles make you lose whatever happens, or at least never win whatever happens. So this is introduction. Now let's turn to sets of desirable gambles. And one way to think of sets of desirable gambles is by a preference order. How it typically works is, say you have a PMF, you have a probability mass function P, then this informs a preference order, which we indicate by the squiggly smaller than, indexed by P. And this preference order may be given by just expected utility of the gambles. So G is preferred to F if and only if the expected utility of G is greater than the expected utility of F. Such an order, it's a strict weak order, so it's a strict partial order. It's irreflexive and transitive. And moreover, absence of the order is also transitive. That makes it a weak order. And furthermore, this order is compatible with vector operations. So if F is this preferred to G, well then scaling every F and G with a common positive real number lambda remains this preference valid. And also we can add a common gamble H to both sides without losing the preference. Now, typically, how people generalize that idea is, well, they talk about preference orders in their own right, and then they typically relax the requirement of being a strict weak order. And they just assume that it's irreflexive and transitive, or in other words, that we have a strict partial order. That's still moreover compatible with vector operations. And this last thing is important because it allows us to infer this equivalence that G is preferred over F, if and only if G minus F is preferred to 0. And this is an important idea because this tells us that the entire preference order, this one, is determined by which gambles are preferred over 0, the status quo is 0, the gamble that leaves your capital unchanged, whatever happens. And so this is so important that it's been given a name in its own. The gambles that are preferred to 0 is your set of desirable gambles D. And so we collect the gambles G that are preferred to F. For such gambles, we collect G minus F in D. And now a set of desirable gambles by this equivalence relation, a set of desirable gambles is equivalent or is an equivalent representation of the same information in a preference order. So that's the main message of this slide. A partial preference order is equivalent to a set of desirable gambles. Now the question is, when is a set of desirable gambles a good one? When does it correspond to rational beliefs? When is it called coherence? Well, one definition could be the order on which it's based is a strict partial preference order. Or in other words, there are requirements on the D itself. If we want to talk about Ds, about the sets of desirable gambles in its own right. And it turns out that it's equivalent to these 4 axioms. The first one says, well, 0 is not preferred to 0. That's quite, plausible, I would say. The second one says that the green gambles from before, the good gambles, all of them should be desirable. The third one says that if I have a gamble that's desirable, well, then I can rescale it by any positive real number and obtain a gamble that's again desirable. And the fourth one is, if I have 2 gambles that are desirable, well, then so should their sum. D3 and D4, these 2 axioms, they turn coherent set of desirable gambles into convex cones. That, moreover, by D2 includes a positive orthant, and by D1 does not include 0 and therefore cannot have anything in common with a negative orthant. So the green set here is a valid coherent set of desirable gambles. This one too, basically any convex cone that includes a positive orthant and has nothing in common with a negative orthant is a coherent set of desirable gambles. And now there are some special ones. For instance, this one. And what's special about this is that this is an open half space. So it's determined by this boundary, and this boundary actually is determined by a linear operator, or in other words, by an expectation operator. And so for any probability mass function P, the set of gambles that have positive p expectation is a coherent set of reliable gambles. We must be careful, we must include the positive ordinate because the probability mass function p might have some zero values in it, and then we might miss some gambles on the boundary. So, but the idea is probabilities are special coherent set of reliable gambles, namely the open half spaces. One important feature that sets of reliable gambles have is that they have a unique smallest coherent one. And the unique smallest coherent one is called a vacuous one, and it's just a positive ordinate. So that's coherence for set of reliable gambles in a nutshell. For the time being, I will keep them on the left. So the left, you can see it as a margin where you can keep notes, because the notation might get complicated if you're not used to it. But on the left, I will try to keep the things that are important. So let's look at some example. The first example could be, well, I have a coin, and I believe that the coin is biased by at most 25%. So now I don't have a precise probability mass function, but I have a set of them rather. And I have this set indicated in blue. And the set is the set of PMFs that correspond to, well, the bias is at most 25%, or in other words, the probability of heads is between 1/4 and 3/4. So I can depict it graphically in this set. How would we build a set of reliable gambles based on this information? Well, one thing to do is I need to ask myself, when do I find a gamble desirable? When do I prefer a gamble over zero? Well, I want to be cautious, and I want to call a gamble only desirable when it has a positive p expectation for every p in my set of probabilities. And when I do this, I obtain such a set of reliable gambles. So gamble on this ray, for instance, this one, this dot, might be the gamble -1,3. That's one on the boundary. And here I would have a gamble 3, -1. Because those gambles have zero p expectation for one probability in this set, or in this set rather. And so we see that set of reliable gambles, the main message is that set of reliable gambles can deal with indecisiveness. They can deal with imprecision. They can deal with sets of probabilities. But not any set of probabilities, as the following example shows. I may believe that I have a special coin, and I believe that it's tricked in the sense that it's biased by at least 25%, but I don't know to which direction. So now my set of probabilities compatible with this belief is this set. So the set where the probability of heads is between 0 and 1/4, union this set, where it's at least 3/4. And now I use the same rule to obtain my set of reliable gambles. But what I get now is that I obtain a vacuous set of reliable gambles. And that is because the presence of this probability 0 for heads. Well, this tells me that a gamble can only be desirable if its heads component is positive. And same one for here. A gamble is only desirable when my tails component is positive. And so combining these two requirements, well, leads me to a set of reliable gambles where both my heads and tail components are positive. But for coherence, I need to include a positive ordinate. So I end up with just a positive ordinate. So the message here is that I lose information by going to a set of reliable gambles. Namely, I use the information that this gap does not belong to my belief, if you want. So I cannot distinguish this belief from the vacuous belief, where I don't have any information, where the set of compatible PMFs is just the complete simplex of PMFs. So I need to do something else. I need to go to choice functions to retrieve this information. So that's what we will do. But first, I will talk about one very important mechanism, namely natural extension. And this is to the heart, I think, of any good imprecise probabilistic model. This really is very important, and it's very nice, I think, because it generalizes both probabilistic and logical inference. So it's the inference mechanism that really rolls out coherence, if you want. The idea is as follows. I may have an assessment A, or I may think about A as a partially specified set of desirable gambles. Maybe an expert told me that what the gambles here are desirable. He or she prefers them to 0, and also they prefer this, for instance, this gamble to 0. That's a partially specified set of desirable gambles. Now, by coherence, by these 4 axioms, other gambles outside of A may be desirable too, just by taking coherence into account. Namely, which gambles? Well, by D3 and D4, all the gambles in posi of A. And posi is the conic operation, if you want. It returns the smallest cone, the smallest convex cone that includes A. So it includes this. Graphically, it includes this green set. So this is posi of A. But not only this should be desirable, I also should take into account D2. So I also should take into account the positive orthons. And now this, E of A, that's a natural extension of A, this is the smallest coherent set of desirable gambles that includes A, or in other words, it's the consequence of my assessment A taking coherence into account only and nothing else. So that's a consequence operator, if you like. We have a theorem about it that's well known. The theorem says an assessment A has a coherent extension, which we call consistent, if and only if 0 does not belong to posi of A union positive orthons. That's the first statement. The second one, if A is consistent, then its natural extension is precisely this posi of A union the positive gambles. So graphically, it's this one. So this E operator, natural extension operator, is very important. For instance, it has, in some way, basis theorem as a special case, or basis rule as a special case. Also, it allows us to think of inference as logical inference in the logic of where I'm allowed to make statements of these things are desirable and conjunctions between them. So that's a very important operator, I think. Just to finish, sets of desirable gambles. I like to mention what the following people. There are many more people who worked about who worked about sets of desirable gambles. But I think these 7 did particularly interesting things. The first one to use sets of desirable gambles was Teddy Seidenfeld in his 1990 paper. But there he used the term sets of favorable gambles. And so he's the first one, I think, to think about sets of desirable gambles in an imprecise-probabilistic context. Then Peter Wally, in his famous book, Statistical Reasoning with Imprecise Probabilities, and in later articles, he further developed the theory. Also Peter Williams, he talked about sets of acceptable gambles. And he developed a well-developed theory about it. Then Gert de Koolman further developed it. He did exchangeability, he did multivariate sets of desirable gambles, independence, together with Enrique Miranda, together with Erik Kwagebeur. Erik Kwagebeur has a chapter in the Introduction to Imprecise Probability book about desirability. Jasper Bock also did many things about desirability. Interestingly, he talked about sets of desirable things. So that's a useful generalization that we won't talk about today. And Enrique Miranda, in his rather new work, he also talks about nonlinear desirability. But to enter the section about desirability, I'd like to talk about real networks under epistemic irrelevance for just 1 minute, because that's work done by Jasper de Bock and Gert de Koolman for sets of desirable gambles, but also for lower previsions done by Marco Zavalon and Alessandro Antonucci and others. And the idea is, we just take a Bayesian network, and instead of taking probability mass functions as local models, we now take sets of desirable gambles as local models. And then we change the local Markov condition slightly. We don't talk about independence, but we talk about irrelevance, which is an asymmetric version of independence. And the idea is that for each node, say x4, conditional on the parents, which is x3, all the non-parents non-descendants, which are the other nodes, are irrelevant to it. And now, if you have a node like here, a structure like here, x3, x4, x5, that means that conditional on the parent x3, x4 and x5 are independent to each other because they are irrelevant in both directions. So if you want to create networks with choice functions, we'd rather have a good notion of independence. So this is one motivation behind the present seminar. Another motivation is, well, I want to know what's the most plausible, what's the best definition of independence. What makes the most sense? So that's the second motivation for why doing the current study. Good. Let's move to choice functions or sets of desirable gamble sets. The motivation, again, to do this is sets of desirable gambles are very nice to work with. Let me go back to this slide. The main message here was they're very nice to work with. There has been big amount of work done about them. They are particularly nice from a theoretical point of view, but also from an intuitive point of view. They give a geometric flavor to imprecise probabilistic reasoning. So they're just a joy to work with. But as we have seen in the example about the coin, they lack some, well, they are incapable of dealing with some certain of basic types of belief. For instance, the coin is biased by at least 25%. So we want to move to things, to models that can deal with these types of beliefs. And that's a choice function, for instance. Now, the idea is as follows. I will consider a finite set of gambles. We'll call that a gamble set. Now, the finiteness is not essential because people like Teddy Seidenfeld and Jasper de Bock have generalized this. But just for simplicity, I will talk here about finite set of gambles. And this gamble is a menu or is a decision problem, if you like. And so I want to ask myself, how do I make decisions? How do I decide? How do I solve my menu? In other words, I want to ask myself which gambles from it are admissible or choice-worthy, and which gambles from it are inadmissible or rejected, not choice-worthy. Well, I collect an R of F, the inadmissible gambles from F, and in C of F, that's a complement, the not inadmissible gambles, or in other words, the admissible gambles from F. If I do so for every gamble set F, then I obtain a rejection function and a choice function. These are equivalent representations of the same information, and I will use them interchangeably. Oh. Yeah. Let's look at some examples. If I have a probability mass function P, well, then there's one obvious rejection function, namely the rejection function that from any menu identifies the gambles F such that there's not a gamble G that dominates it in expected utility. That's famous, of course, that's expected utility maximization. But this induces a rejection function. Now, in the second example, I may have a set of reliable gambles D or a partial preference relation. And then I can use this directly to make decisions. And one typical way to do it is I identify my R of F, while I identify the rejected gambles, the dominated gambles in F. So the gambles F for which there is a G, such that G is preferred over F. And then, of course, G is preferred over F, if and only if, according to this definition, F is rejected in this binary choice between F and G. Now, as the third example, I may have a set of PMFs, which I indicate by this M. For instance, I have the set from before, about my coin example. Well, then I can use admissibility to make decisions. And how this works is, well, in my rejection function f, I identify the gambles f in the menu such that for every p, there is an f that's a winner. In the sense that, sorry, for every p, there's a g that's a winner. In the sense that for every p, there's a g that has a highest, that has a higher expected utility, p expected utility than f. And of course, the complement of this, the choice of f, is the union over all p of the winners. So that's e-admissibility. And now this is a very interesting one, because e-admissibility, typically, it's an instance of non-binary choice. In the sense that it may happen that f is admissible between f and g, and also it's admissible between f and h, even though the presence of g and h together make f inadmissible. And we'll see an example of this in a few minutes. Namely, in this example. Again, let's revisit the coin example, where I believe that the coin is biased by at least 25%. Then my set of probabilities may be this one, so the union of this interval with this interval. We've seen that with set of desirable gambles, we cannot distinguish this belief from the vacuous model, from the vacuous belief, but I will convince you, or try to convince you, that with e-admissible choice functions we can. And to do this, consider two gambles, f and g. So f is a gamble that gives you 1 in heads, -1 in tails, and g is the symmetric version of it. Now I'll draw here a diagram that Tijdi Seidenfeld often uses, and I've used this diagram from him. What I draw here is, on the axis, I denote the value of the probability in heads. Now, since the probability in tails is it's 1 minus the probability in heads, a point on this, for instance, this point, this completely determines my probability mass function. So it's the same as here. And then on these red lines, say this one, I'll draw the expected utility of the gamble f. Now, if it's the probability in heads is 1, its expected utility is 1. But if the probability of heads is 0, its expected utility is -1. And then here on this line, we have the expected utility of g, and I will contrast it with the expected utility of the constant gamble 1/3. That's of course 1/3 whatever happens. Now, e-admissibility can be read off from this diagram. More specifically, the admissible set from the menu that consists of these 3 gambles can be read off. How do I read it? Well, I just look at each probability in the blue area. That's my belief. And I look at, for each probability, which gamble is a winner. So I see this red one, G is a winner here, and the gamble F is a winner here. Crucially, the gamble 1/3 is no winner, because it's only a winner for these probabilities, but these probabilities are not in my belief. So I see that 1/3 is rejected from these 3 gambles. But of course, if I had a vacuous belief, then I would add all these gambles also to my belief, and then the gamble 1/3 would be a winner, namely here. So this rejection function, this choice function based on e-admissibility, is different from the vacuous choice function, where 1/3 would also be a winner, would also be admissible. Now, in order to work with choice functions, rejection functions, in a mathematically more easy way, we will move to sets of desirable gamble sets. And the idea is very much like the way of moving from preference orders to sets of desirable gambles. And the way it works is like this. Let's call Q the set of all gamble sets, the set of all finite set of gambles. And let's assume that all my good rejection functions R or choice functions C satisfy this property. F is rejected in a gamble set if and only if F minus G is rejected in a version of the original gamble set where I subtracted G from every gamble F in my gamble set, in my menu. So this is not very well, I think it's a plausible property for rejection functions. Now, if we have such a property, then I can completely specify R by looking at which gamble sets are such that 0 is rejected from it. How this works is, well, if I have a gamble set F and a gamble small f in it, then this gamble f is rejected from the gamble set, if and only if 0 is rejected from the new gamble set. And if this happens, we call f minus this gamble a desirable gamble set, well, simply because 0 is rejected from it, and we take this to mean that, well, this gamble must contain some gamble that is desirable. We may not know which one. We may not be able to identify which one. So, but now this allows me to do the following. I collect in K, my set of desirable gamble sets, all the gamble sets that contain at least one desirable gamble. But importantly, I may not be able to identify which gamble is desirable. And conversely, if I have such a set of desirable gamble sets under very, very mild assumptions, I will be able to retrieve the original rejection function. So the message here is that K, a set of desirable gamble sets, and R, rejection function, they are two equivalent representations of the same information. So from now on, I will work with set of desirable gamble sets K. Again, that's a set of gamble sets that contain, well, and a gamble set belongs to K if and only if this gamble set has at least one gamble that's preferred over 0, but I may not be able to identify which one. That's the idea here. Now there's, again, coherence, rationality axioms about it. I use the one that Jasper de Bock and Gert Koolman used earlier. They are slightly different versions from it. The first one were identified by Teddy Seidenfeld. But let's quickly discuss these. Again, the interpretation is K. A gamble set belongs to K if and only if this gamble set has a desirable gambles. Of course, this informs my first action. The empty set can never have a desirable gamble, of course, because it's empty. Second one is, if I have a desirable gamble set, F, this means that F must contain a gamble that's desirable, then this gamble that is desirable can never be 0. So we may safely subtract 0 from it. K2, the third one, says that, well, if I have a good gamble, these gambles form desirable gamble sets on their own, singletons. K3 is the most difficult one that allows us to combine two desirable gamble sets, F and G. And it's in the following way. If F is a desirable gamble set, then it means that F contains some gamble F star. I don't know which one, or I may not know which one, but it has a gamble F star that's desirable. The same for G, it has some gamble G star that's desirable. Well, by running over all the gambles here, multiplying these gambles with positive coefficients and adding them together, I will again find a gamble that's desirable. I may not know which one, but by running over all of them, in this way I obtain a set of gambles that's desirable. That's a desirable gamble set. K4 is really not very controversial. It says that if F contains a desirable gamble, well, then any superset of it also. So that's coherence. Instead of working with coherence on its own, there's a very useful and very surprising to me representation result. And in order to explain it, I will go back to Stan-Woolley maximality. So we'll go back to a set of reliable gambles, D, and we'll use this to make decisions in the same way as before. So remember, my rejection function based on D identifies all the gambles such that there is a G such that G minus F is desirable. In other words, it identifies the gambles F for which there are other gambles G preferred to F. Now, if we translate this to a set of desirable gamble sets, to KD, I get the following formula. Turns out that, well, it's very easy. Just plug in, that's the definition. Plug this in here. So KD collects all the gamble sets such that 0 is rejected from this gamble set. In other words, such that there's a gamble F in this gamble set that's also desirable. Or in other words, such that this gamble set intersects D. Those KDs are very important. We call them binary Ks because they are completely determined by a binary preference order, by a set of reliable gambles. And these, such KDs, well, they completely represent coherence in the following way. Consider any set of reliable gamble sets, not necessarily coherent, then the following two expressions are equivalent. The first one is K is coherent. The second one is there is a collection of coherent sets of desirable gambles such that K is an intersection of this collection, of the KDs based on this collection. And in this case, we call this set D of coherent sets of reliable gambles a representation of K. Moreover, any coherent K has a unique largest representing set, and I'm just looking at the coherent Ds for which KD is above K. So that's the largest representation. K may have different representations, subsets of this one, but it always has a unique largest one. And so that's important because it allows us to look at coherent choices, coherent set of reliable gambles, in a more structured way. Let's look at two special cases. The first one is K has a representation, D, that's actually where every element of D is an open Hall space, or in other words, it's determined by PMF P. In this case, we have E-admissibility. So E-admissibility is a special case of coherence. And when is it a special case? Well, exactly when it has a representation where every element is an open Hall space. The second important special case is K is represented by a singleton. In such a case, K is KD of the singleton, of course, and then we retrieve Stan-Woolley maximality. And so by looking at these two edge cases, we see that coherence in general is a combination of these two. It's typically not represented by a singleton, but by a set. But the set typically does not only contain open Hall spaces, but also more general coherent set of reliable gambles. And so therefore, loosely speaking, we can look at coherence as the admissibility of more general models and probabilities. So that's one way of looking at coherence. Now, this is the last slide about choice models. It will become more concrete after this in part 2. But the last slide is about natural extension. So remember before, for sets of desirable gambles, if we have the idea of natural extension is we have a partially specified set of reliable gambles. Its smallest coherent. It always, if it has a coherent superset, it always has the smallest coherent superset. And the same idea applies here. It's much more complicated by looking at coherence directly, but actually by looking at representation, by this one, the previous slide, this simplifies things a lot. So the idea is, I have a partially specified set of reliable gamble sets, calligraphical A, well, then this A is consistent, has a coherent superset, even only if it has a coherent binary superset. So that's surprising to me, but it turns out true. And moreover, if A is consistent, then it always has the smallest coherent superset, and that's just the intersection of all its dominating binary ones. So this, is a very easy way of talking about natural extension. And it's very surprising to me because it tells us that I have a partially specified set of the Campbell sets. In order to find all its implications using coherent and coherent alone, I just have to look at its binary supersets and take the intersection. Now, set of reliable Campbell sets are important. They are popular. Many people have worked on it. The first work in the imprecise probabilistic literature has been by Teddy Seidenfeld, I think in 2007, where he looked at choice functions that moreover are coherent, but are moreover mixing. More about this in a few minutes, and are Archimedean, and he obtained a representation in terms of not necessarily convex set of probabilities. Then Gert de Koolman, myself, Enrique Miranda, we have built on this work and looked at choice functions for Campbell's, the one we're talking about now. Jasper de Bok, his main idea was to look at K's, set of desirable Campbell sets, and later to generalize it to things instead of Campbell's. Catherine Campbell-Moore has a very promising, very nice, beautiful characterization of choice functions in terms of probability filters. She has papers about this, and she started this work with Jason Connick. Now, Jason, Kevin, and myself, we have looked at epistemic independence, so one of the types of independence in part 2 that I'm going to talk about for choice functions. And lately, Arne de Kat and Alexander Ergens, together with Jasper de Bok, they have been looking at inferences with choice functions. That's also very interesting and promising work. So, but my main message here is that choice functions are nice to work with. They're very general, but also mathematically elegant. And so there are many research topics open that are, I think, nice and perhaps fundamental. So if you're ever looking for a nice research topic, probably choice functions would be a good contender. And because these people are currently working on it, there's much interesting work being done currently, and I hope it will continue in the future. Good. I think I have some time to talk about independence. It's much shorter, much easier. But this is the second part of my seminar. Remember, I will talk about the 3 notions of independence, which we identified before. And I will do so in a context where we have 2 variables that have finite possibility spaces, x and y. So I have 2 variables, x and y, and they each have a finite possibility space. The first idea is epistemic independence. And epistemic independence comes apart into irrelevance from x to y and irrelevance to from y to x. And the idea is the following. We have irrelevance from x to y if learning that non-empty event about x obtains does not affect my beliefs about y. So if I have a set of desirable Campbell sets, this amounts to the following. My y marginal for x after conditioning on this event is the same as my y marginal for k. So this expresses that learning that Ex obtains doesn't matter for my decisions that only depend on y. That's epistemic irrelevance from x to y. The symmetric version is symmetric irrelevance from y to x. And together, they are called epistemic independence. Now it turns out, by an earlier paper, that given 2 coherent marginals kx and ky, these marginals always have many epistemic products, or at least one, typically many. An epistemic product is a coherent k joint k that satisfies epistemic independence and that has these 2 models as marginals. Now, importantly, it always has unique smallest epistemic product. And this smallest epistemic product is denoted by this. This O times is, I inherited it from a paper by Gert de Koolman and Enrique Miranda, where they did the same for desirability. So this is one idea. This is one theory of independence. It's fruitful because we have an independent natural extension. So again, if we have two marginals, we can look at the smallest joint that has these two margins as its marginal, and that satisfies this notion of independence. I'll quickly discuss the same setup for the next two notions of independence. The first one is a new one. We've submitted it to a paper for IPMU that's recently been accepted. And I did so with my co-authors, Justina Dombrovska and Banda Norimarne. And the idea here is that, well, we call two variables independent if their model has a independent representation. So a representation whose every member satisfies independence. And this is very natural for K's. Because remember, every K, if it's coherent, has a representation in this sense. A representation in terms of a set of coherent sets of reliable gambles. So the requirement here is, well, we say that the coherent K satisfies representational independence if K has a representation D where every element in D satisfies epistemic independence. It turns out that this is a fruitful idea in the following sense. Again, if we have two marginals, Kx and Ky, we call a joint K that's coherent and it has these two marginals as its marginals, a representational product if it satisfies representational independence. And it turns out that if we have such two marginals, there's always the smallest representational product of these marginals, and this smallest representational product is given by this intersection. So we just look at the largest representation for Kx, the largest representation for Ky, we combine them using epistemic independence for desirability, and take these intersections. Now that's different from the epistemic independent natural extension. So they come apart. The third one is started by Teddy Seidenfeld in his 2007 paper, but it's further developed by Jasper de Bok and Gert de Koolman. They coin it as irrelevance, and the idea is really plausible to me. The idea is that, well, if a variable y is irrelevant to a variable x, then it should mean the following. It should be irrational, it should be inadmissible to spend resources in order to use the observed value of y to make decisions between gambles that only depend on x. So that's as irrelevance. And so we can translate this easily with choice functions. We can't do this with sets of reliable gambles or less expressive models because we really have a choice between 3 or more gambles. So it's really a non-binary choice. And the idea is as follows. I model my observation of x by a partition of x, and I assume that I can observe every element in this partition. And now for every element in this partition, I have a potentially different gamble, Fe, that depends only on y. Now the action of first observing x and then selecting such a gamble on y, this corresponds to taking this composite gamble. This is the indicator of E, so it's only activated if x belongs to E, it's 0 otherwise. And if x belongs to E, so if the event E obtains, well, then I play this gamble, Fe of y. And now paying the price epsilon for this, well, it's playing this gamble minus epsilon, of course, because you lose epsilon. That's paying epsilon for this gamble. Now the requirement of S irrelevance now is that this gamble F should be inadmissible, should be rejected from all the non-composite gambles Fe, all the atomic gambles if you want. So in other words, the requirement is for any partition P, for every real epsilon, and for every choice of gambles Fe that depend only on Y, this should be desirable gamble set. And this is just this gamble set, this menu, this option set, but where we subtracted F from every element from it. Because then we have 0, it's rejected from some gamble set. And so S independence is requiring S irrelevance in the both directions. And now it turns out, which is something that my co-authors and me have done, it turns out that, again, if we start with two marginals X and Y, we call any coherent K on the joint space that has these two models at its marginals, and that moreover satisfies S independence, while any such K, we call it an S product. It turns out that whatever marginals we start with, there's always a unique smallest S independent product. And this S independent product is given by much the same shape as before, but I need to make some caution here. First, we need to assume that these marginal ones satisfy two more axioms, namely mixingness and Archimedeanity. Mixingness is requirement this one. It allows us to infer the desirability of some gamble sets. From the desirability of some gamble sets, the desirability of some subsets. When can we do this? Well, when the subset has the same convex hull or the same conic hull, if you want. But the subset just is taken, this F is taken, it's built from G by taking some gambles in G that belong to the pose of other gambles in G. It turns out, that's a result by Jasper de Bok, Gert Koolman, that a K is mixing. If a K is mixing, then it's represented by mixing these, by which we mean the complement also the convex cone. So it means that the D's are very big. They are also half spaces, open half spaces, or even things on its boundary. That's mixingness. It's something that Teddy Seideveld endorses, and that I'm, at this point, don't know if I want to endorse it as a requirement of rationality. The second one is Archimedeanity. The main message is that it has as a consequence that K is represented by a set of lower previsions. Now, by combining Archimedeanity and mixingness, we get that K is represented by a set of lower previsions that are moreover almost precise or precise. So in other words, it's represented by a set of linear previsions. We call this P underline. That's a representation of Kx in terms of linear previsions. And it turns out that the smallest S-independent product is just by taking any linear prevision in the representation of both its marginals, combine them by just taking the product. So we have independence, then build a D of it, and then build a K of it. And then take all these intersections. So that's an inference or a theory of inference with S independence. Now there are two main, this is the penultimate slide. There's an interesting connection between representational independence and S independence. And the first one essentially is already given by a paper of Jasper de Bok and Gert Koolman. It says if K is Archimedean and it has positive probabilities for every outcome, that's just a technical requirement that we won't go into detail here. But if this happens, well, then S independence implies representational independence. And the idea is that any such K, if it satisfies S independence, then any such K is mixing. And to me, that's a really surprising result. So we get that any coherent K that satisfies S independence has a representation in terms of half spaces, where every element is a half space. And then, of course, S independence makes it so that the half spaces are independent. And therefore, we have a independent representation, so we have representational independence. Now, conversely, interestingly, turns out that if K is mixing, then representational independence implies S independence. So that's also something nice, I think. So they are really closely connected. Now, I end my presentation with some questions, perhaps more questions than I would like. But the first important question, or first interesting question to me is one that was already identified by Jasper de Bok and Gert Koolman. Should mixingness be a requirement of coherence? Terry Seidenfeld seems to think so. I'm less committed to this. But if we think that as independence is a good definition, well, for any problem, I think you can find something that's independent about it, that's independent to it, or maybe even only irrelevant to it. If then this irrelevance is taken to mean as irrelevance, then mixingness would follow. So it seems, one way of this argument seems to say that if as independence is plausible, then mixingness should be a requirement of coherence. Perhaps we could make the converse argument. If mixingness is not a requirement, it's too strong, it's not a requirement of coherence, then maybe as independence is also not a suitable definition. But to my mind, this seems hard because it seems so plausible to me that as independence is a good definition of coherence, but I would love to discuss about this. Now, second idea is, if we want to use independence in Creedal networks, what properties do we want to have? One of them is that we need to be associative. Unfortunately, we don't know for any of the products whether or not it's associative yet. The second one is, ideally, we want the representation to be of the same type. For instance, look at representational products. Here, the inputs are, we start with the unique largest representations of the marginals. We obtain a representation, this one, of the product. Now, this is typically not equal to the largest representation. So we cannot use this again. If we have a kx and ky that are representational independent, we may obtain the smallest representational product. But if we then have a kz that's also representational independent to it, we can't use this again, or we can't use this representation again, rather, to obtain the representational product of the three. That's just because the reason is we don't have the largest representation of this one. We don't know what it is. That's related to the problem of associativity, by the way. Then the last one is another requirement I think we want to have is that for probability mass functions, the three concepts of independence coincide. And luckily, that is the case. So that's a result in our paper. If we have two probability mass functions with positive probabilities, again, a slightly technical requirement, well, if I use then, say, using the admissibility based on a singleton, if I build a KP and a KQ, then no matter how I combine these ones, I always obtain the same joint, and the same joint is equal, moreover, to the admissible one built on the product of these two mass functions. So that's, to me, a very necessary requirement, but luckily fortunately, it's met. Good. This was my seminar. I'm very happy. And I'm also very happy to take any questions or to know your thoughts about the questions I posed.